Okay, so let's have a look at solving this game backwards. And solving it backwards, what does that mean? So we'll use a backward induction algorithm. So what does that mean? That means that we will start at nodes that are followed only by terminal nodes. So the last choice is to be made in the game in a well-defined sense. We'll choose a strategy that maximizes payoffs or utility for the players at those points. Then specifying those strategies, we'll move back to nodes that just precede those and look at what people would do at those points and then iterate, move up the tree and repeat. So we're just solving the game, literally just unfolding it backwards up the tree. So what do we end up with in this particular structure? So if we look back at our entry game, when we look at the choice of the existing firm in the market at the last point, so this is a node where the choice is all the choices of this at this node lead to terminal nodes. So in particular, what do we end up with? We end up with 0 if they fight, profit pi, which is greater than 0 if they accommodate. So the only prediction that we can make in terms of a player maximizing payoffs is to accommodate. So when we have we back up the tree, now when player 1 makes a choice, they can anticipate what 2 is going to do if 1 enters. We started by analyzing 2's choice, and more generally, we'll always be just looking down the tree, solving it backwards, and having players anticipate what's going to come next. So in this particular case, now that we think that player 2 is going to accommodate, so essentially we can ignore this part of the game. So player 1's choice becomes a choice between 0 if they stay out, positive profits if they go in. Remember, pi is assumed to be bigger than c. So now we end up with a prediction of enter and accommodate. So the backward induction solution in this particular game is unique. It tells us that player 2 will accommodate, player 1 will necessarily enter, so we end up with a prediction of enter and accommodate. So generally when we look at backward induction, if we're working with these games of perfect information, if players are never indifferent between options, then it will give us a unique prediction. So players will always have a single strategy at every particular node that maximizes their payoff. And then we have a unique prediction at every node. We can back up the tree. We end up with a unique prediction overall. So the only difficulty in terms of backward induction, when won't it give a unique prediction, is situations where some players might be indifferent. And maybe then it can predict that they pick one strategy or another or mix. So then the prediction is a little less stark. But more generally in most games, in the sense of games where you don't have exact indifferences between different possible outcomes, then we will end up with a unique prediction from a backward induction solution. So it's a very powerful tool in games of perfect information. It's giving us a unique prediction of what should happen in this game. So let's have a look at how the backward induction solution compares to Nash equilibrium. So when we looked at the backward induction solution, it said enter and accommodate. That is a Nash equilibrium, right? So if firm 1 enters, firm 2 is best responding, accommodating is the best response. If firm 2 would accommodate at this node, then firm 1 entering is the best response. So it is picking a Nash equilibrium, but there's also another Nash equilibrium that is not found by backward induction, right? So what do we end up with? We end up with a set of Nash equilibria including more predictions, some of which are not predicted by the backward induction algorithm, whereas backward induction algorithm always predicts a Nash equilibrium, but it might not predict all of the Nash equilibria. So there are some games where there's more Nash equilibria than the backward induction solution. And in particular here, the one we solved for before, where firm 1 stays out, anticipating that firm 2 would fight if they entered, this is not found by backward induction. This is a Nash equilibrium, but it's a Nash equilibrium only because firm 1 believes that firm 2 is going to do something which is not in firm two's interest. So firm two is not maximizing their payoff at the second node. Now, just in terms of understanding the predictions of this game, you could imagine that in the real world, when we begin to apply this to different settings, that that the second player in this sort of game would want to posture and convince the other player that they're actually going to fight and so forth. And the question is whether or not they're really rational or not. And this kind of reasoning is putting a high premium on the fact that the second mover is going to act in their interest and not do something which is against their payoff interest. And we'll see that there are settings which differ from this game, that if we allow for some repetition of this or other kinds of variations on this game, then we can begin to change the nature of the outcome. But in this particular one-shot setting where the firms each make one choice and that's it, then indeed this is not a prediction which is credible, in the sense that firm two shouldn't fight if firm one enters. It wouldn't be maximizing its payoff and is foregoing profits. So we end up with enter and accommodate being the backward induction solution.